The new tools that calculus developed were so powerful that much of science and mathematics in the 1700s was basically just finding new ways to apply two really basic, when you get down to it, concepts. So let's look at the two main branches of calculus and what they're used for. Calculus is really just two main ideas. There are a lot of other things behind them and going into them, but really we're just going to be mostly talking over the course of the year about something called the derivative and the integral. Let's first give you the notation for each. The derivative can be notated several different ways. Gottfried and Leibniz and Isaac Newton both developed their work somewhat independently, and they used very different notation for it. And today we still use some different notations for the derivative. But basically both of them, or all three of them, are more convenient at different times, so they've still persisted today. So this is read as d dx of f of x. This is dy dx. And this is f prime. That little symbol isn't a 1, it's a prime of x. These all mean the same thing. They all mean the derivative. And we're going to talk about what the derivative is soon. The integral really only has one notation that's left at this point. This would be read the integral or the antiderivative of f of x dx. We're going to start with the geometric notation, or excuse me, the geometric definition. Of each of these. So the derivative is the slope of the line tangent to a curve at a given point. So to draw a picture of that, this is f of x, this is x. We have some funky little curve here. The tangent line separate that out so you can see it a little better, is the line that just brushes the curve at the given point. And all the derivative is the slope of this line, just like we were working with when we were talking about the differences between calculus and pre-calculus on the previous page. The integral is the area, so this is area instead of slope, bounded by the graph of a function from x equals a to x equals b. Notice that the derivative is taking place at a point, whereas the integral is from one to another value of x. So, sketch that, x, f of x. We've got our little funky curvy shape. The area under the curve from a to b, whatever value of x, a, and b are, area under the curve, or the area bounded by the curve, these two lines, and the x-axis. So really when we're looking at integral, we're talking about area. When we're looking at the derivative, we're talking about slope. Those are the two basic ideas in calculus, and they're also the ones that we were talking about on the previous page. So let's do a couple of examples where you're just going to identify whether or not we're working with the derivative or the integral, and then estimate what the values of those are. So right below here, let's write examples. First, on the curve at right, sketch a line tangent to the curve at x equals 1. So here's a little graph of what we're going to be working with. You can grab some graph paper, do a little sketch of this, or if you can put up the paper up to the computer screen and sketch it off there. When I give you homework problems, I'm going to give them to you on graph paper, so you want to get the idea from this. Sorry, this should be x equals 4. Tangent to the curve at x equals 4. So the idea with the tangent line is we want to just barely brush this curve. And we want to do it right at where x equals 4. So that's this point right here, x equals 4. By coincidence, y also equals 4, but I'm looking specifically at x there. And so what I'm going to do is grab a straight edge and basically try to take that straight edge and put it where it just barely brushes that curve. So about like that. This is going to be an estimate. So if it ends up a little bit differently, that's okay. But there we go. I've just sketched a little tangent line right there. Now what I want to do is I want to estimate the slope of the tangent line. The slope is change in y over change in x. So here's my little line. I'm going to take 1 point here, 1 point here. I could have picked these points. It's whatever, it's fine. Change in y, I went down 2. Change in x, I went right 1. So change in y over change in x is negative 2 over 1. Negative 2. Notice it's sloping down, so it's going to be a negative slope. And then C, have you found the integral or derivative? We know that the slope of the tangent line is associated with the derivative. So that means we found the derivative of, this is called f of x, at x equals 4. And there we go. That's calculus. There will, of course, be a lot more to it, but that's the basic idea. Okay, let's do another one, working with the integral this time. On the curve at right, shade the area under the curve. You'll see this phrase under the curve a lot. It really means bounded by the curve and the x-axis from x equals 3 to x equals 5. Let's make that x equals 6 for kicks. 6. There we go. Okay, so the area under the curve, from the curve to the x-axis, from x equals 3 right here to where x equals 6 right there, we're talking about this area right in there. And now, similar to what we were doing before, let's estimate this area by counting squares. So this means you might not come up with the exact same number that I do, but it should be in the right general vicinity. So each square is 1 unit wide by 1 unit high, so it's 1 square unit right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little squares. And you can see these if I go and draw them back in again, because I got a little covered over when I was doing the shading. You can see there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 whole squares. And then up here we can see we've got part of squares. So it looks like there's about half a square there. There's about half a square there. There's a little more than half a square there. So I'm going to say that we've got our 12 here. This one and this one, probably when we put them together, that's about another square, so that's 13 total squares. And then this looks like more than a square, so, or more than half a square, so call it 13.6, 13.7, 13.8, somewhere between 13 and 14 little squares. Really between probably about 13.5 and 14. So that's all that is. That's estimating. That's the basic idea of what we're doing, just finding the area under the curve for calculus. And then let's ask, did you find the integral or derivative? Remember from the previous page, the area under the curve is associated with the integral. So that means that we found the integral of, this is f of x again, from x equals 3, that's where we started, to x equals 6. That's where we ended. Notice that the derivative is at a single number. The integral is from one number for x to another number for x.